So here I'm going to talk about the 18K story, but I have to discuss a bit about our site, what we are at CA, what we are doing, and why a few years ago we are looking for flash file system. Like I have told you, we have two compute centers. The first one, the defense, which code name is Terra. I don't know if you know the name. The second is the TGCC for European compute centers, where we host DNA sequencing data. It's a big project in France. We host also the CCRT. I don't know if you know this. That's a specific supercomputers which is dedicated for the industrial companies. Then we are proud to host a coming soon project, which is the Human Brain Project. So that's a news project which involves many kind of I/O. So there were many problematics that is very interesting. And to play with the software, with the hardware, we have also compute centers where we are doing R&D on the compute nodes, but also on the storage nodes, the storage cluster, and so on. Some numbers about the compute power. You can see that we are close to 20 petaflops on each site. And for the lab compute centers, we are close to 1 petaflop, but on the lab compute centers, we have many heterogeneous nodes. So that's the sum of all power we have. Of course, when we have these two compute centers, we are doing the same thing about the architecture. Why? Because it is the same guys who administrate, build, and support the solution. So we need a common architecture on each site. That's a typical graph schema we have. We have a data approach architecture where we put the storage at the center of all our resources, like the compute nodes, like the HPSS backend, for example, with the tapes, like a visualization cluster, and so on. Today, we are going to focus on the small circle with the flash storage. Actually, we are running Lustre 2.10 with Lustre HSM. The goal is to hide the complexity to have a second tier in Lustre. So Lustre HSM is doing this stuff. About the Lustre version, we are going to upgrade in Q1 2020 in Lustre 2.12.3, the LTS version. You have some numbers where you can see that you have some bytes of data, some throughput also. These numbers are usable numbers. So the white is not the raw white, it's the IOR white, and the number is the formatted capacity, which is available in the cluster. Next, in numbers of 18K of DDN servers, because you have seen that we have not only DDN appliance at CA, we have also Cray file system. But anyway, here you can see that we have 13 SFA 14KX in production, with each one has 10 enclosure. So the topic of today is about T1KF. T1KF, that's a common slide we have. The target was 1 TB per second in 5% of time in wide sequential. So wait, we need to mount the file system by all supercomputers, and we need to migrate the data between the HDD and the flash. So this part will be done by a tool which is built at CA, Robinhood. And we would like to have a seamless integration like the Lustre HSM feature. Why we would like to do this? Because we have seen that we have two main workloads, wide sequential and random read. So you can understand that random read is pretty efficient on Flash, but for wide sequential, you can ask to me that's not very relevant, because now if you obtain thousands and thousands of drives, you can achieve 1 TB per second without drives. That's quite easy. It's just a question of a number of drives and also money. But we have an issue at CEA. It's that in the defense center, we have a problem of space. It means that we would like to have a density solution. So when you build a solution, we need to just not to focus on the performance, but you need to watch external things like the weights, like the power, like the cooling. Okay. So before to do the history of our flash system, I would like just a quick slide to explain how we work to build the solution. In fact, that's pretty easy approach. I call it layers by layers, because we start from the lower layer and we go up and up on each layer. So, for example, we start with SSD drives. Then, okay, we have to send the SSD, but we need to look at how does it work on the drive protocol, like SAS or NVMe and so on. All this works? Yes. Okay. The other parameter which is important when you want to build a storage area is the network. Of course, you have to choose a network interconnect to connect your data, of course. And after that, you have the drive, you have the network. But what is going on when the data goes through the PCIe buses? There is either any bottleneck or all is fine, the throughput is expected or not. So when you have that, you can begin the raw device I/O benchmark. And finally, you can do the network performance benchmark, and finally, the Lustre file system benchmark. It's easy. So the story began in 2016. Why? Because we have seen that we have many codes which produced many and many bytes. So we were pretty convinced that we need something faster. I don't like the terminology faster, but you can understand the word. Anyway, okay, we work with DDN and with other vendor, but for DDN, we had a beautiful 14KE with SSD drives inside the head enclosure, and we start to run some tests. It takes 3 or 6 months, and we have created 2 issues. The first one, which is when you have placed some drives on some slots, you have bad performance. So it was fixed by a firmware enclosure upgrade. And the second one, when you are doing a storage area, you want to have the same performance between your LUN or OST if we jump into Lustre terminology, if you want. Because you can't have an unbalanced file system. It's unmanageable. Sorry. To sum up, you can see on the red line the modification. In fact, the 3.1.2.1 version A, if I remember, that's a beta version, but this version has implemented a new SAS load balancing algorithm, which fixed the issue we triggered. That's pretty important in the SFA appliance. So story continue. In July 2017, 14KXE is available, so we switch to it, and that's the beginning of the this year feature. So we were proud to be one of the first to test the this year feature. And what we would like to do also is to have some performance drive. On the last slide, the drives was about wide performance to 600 megahertz. So what's good, but not enough for our needed. So we bought Hitachi SS200 drives, which are pretty performant. We are close to 1.2 gigs in wide sequential workload, so good. But we have quickly seen that we need one feature. That's the unmapped feature. Okay. Why? Because the SSD is not a magic toy. Okay. It's harder than when we can think. Okay. When you write on the NAND cell, at one time you have some mechanism inside the drive where you need to refresh the cell. That's the unmapped operation. So we need this. If we don't have this feature, we have many performance degradation. So the story continue. In January 2018, we have decided to choose the 18KE because at CA we are challenging people and we want innovation. That's the first answer. But the real answer is that the 18KE allow us to have a great density. Okay, we take the decision to choose the 18KE. Nothing exists at DDN. It's just on the specification. But we can start about deep drives, bench of drives. It's why we bought SS300 drives, which is a bit costly, but the performance in white is pretty high. We are close to 2 gigs on the drive. But 2 gigs is not possible in the SAS3 version because you have the limitation to 1.2 gigs, of course, due to the maximum SAS bandwidth on the SAS3. Anyway, in July 2018, we have a short list, two candidates, the SS530, sorry, and the Samsung drive, the PM1643. If you want to benefit the throughput of the drives, you have to use both ports, both SAS ports. But in the SFA OS, to allow this, you need one feature, which is the multiple VD feature, which allows us this mechanism. It's pretty cool because in July, this feature was released. One important thing is that we work with DDN about the unmapped design. So we are pretty close to the end. November 2018, we had one of the first sample of the 18KE where we can start some tests about if the system is stable, how was the performance. So to sum up, I have bought some keys. First level, to improve the throughput, we use loopback cables, which is a great feature on the 18KE architecture, which allow the system to boost the performance. I have a graph just after. And it was a sample. It was not pretty stable. We had some crash sometimes, but for a sample, we can say that it was pretty stable. Anyway, the story continues. In January, we are pretty close to choose the drives, but we are still fighting with the 2 drives we have selected. And in January, we found the root cause about the instability. It was a problem of the heat sinks inside the board. So it was fixed in the GA version, of course, but that's cool. In January, we have seen something. Some people said me I am a bit too demanding, but we have some cool performance about the SAS backplane. But I said to DDN, something goes wrong. We can do much better. So it's why we can investigate why we have a limitation on the SAS. In April, we have finally chosen the drive, which is the Hitachi SS530, which is a good drive. About the benchmark we use to choose drives, you can do many bench, watch sequential, read, mixed I/O, and so on. So this kind of test you can do. You can do this test because the vendors has some specification, and one thing what you can do is to check if it's true or not. But it's not sufficient for us to choose a drive. That's the next slide. In fact, on the lab, we start the first Lustre wide sequential bench to check if Lustre is working well or not. The good thing is that in July 2019, the Unmap feature was GA, so it was a good news, and we start to receive the first 18K for production. At this moment, we begin to understand how the IO 500 is working. One side we have used to choose the drive is this one, plus all the bench we did on the drive. That's a methodology that not run, which is used also by DDN team drive qualification, which is the XSR methodology. The goal is to observe how the drives yes, take time to recover from its initial throughput. Here you have 3 drives. You have 2 PM1643 drives, and there is a main difference. One drive has a lower power, and the third one is the 3DWPD Hitachi SS530. Of course, you can check that about the throughput. The first one is better, but is there a pointer here? No, no pointer. Which one? Oh, okay, great. Here, you write in 2 hours in sequential write, and after these 2 hours, you switch to random write. And after these 2 hours, we switch to sequential write, and you measure the time that you put to recover from the initial throughput. So the goal is to have a drive which minimizes this time. That's one thing. What you can see here is that we speak often about endurance and so on, the number of bytes we could write on a drive, but also the endurance has a good effect about the workload modification about the I/O. You can see here after the 2 hours step of sequential write that the throughput doesn't go down when we switch to random. So you have here 10 minutes where you have the full throughput of the drive. So if you have a file system where you can't guarantee that you will have every time sequential write, random write, etc., you can choose if you have the money, because it is not the same price, but you can choose a disk with an higher endurance, okay? Because you can understand easily right now. So we are pretty close to now. We switch to October, because in October we have the full system integration. We have 1618KE with 56 drives. And we had some issue on the InfiniBand network where we couldn't achieve 1 TB per second. So we had to troubleshoot a bit. We have also some failure, for drive failure, for power interposer failure, which is pretty new from engineering. So we are working with DDN to understand what is going on. And we have also one wire card failure. In November, we upgrade all system in 11.6.1, and we could run our first full benchmark. But like other time, we aren't very lucky, because after just before to push the enter command to run the benchmark, we had one canister failure, one disk failure. So you can understand that it takes time to recover the full performance. That's the life. But we could run IO 500 benchmark. You have the results here. The results will have been submitted to IO 500. So that's an official one. You can say that in this case, we have a score to close to 200, which is good, not excellent, but that's not too bad due to the fact that you use Lustre 2.12.3 LTS version, where you know where there is some limitation about unaligned I/O. You can check here we are close to 800 gigs, but unfortunately during this benchmark we had some slow drives where the latency is pretty high, so that's alive also, but the number was pretty not too bad. About the acceptance, we jump to 11.09 TB per second. The IO parameter is not the same as the IO 500, but when we run this acceptance run, we have a lack of time. It was honestly, this run was just achieved one time. Okay, we just run. Okay, we push the button and we wait for the results. What we can say is that it's not a 10-second run; it's a 10 minutes run. So that's the real throughput system the solution can do. But we have space. In fact, we have space. We can do 1.2 TB per second without any issue. The major issue here is that we use buffer I/O, which is not a good approach. But anyway, we are talking during the history about key feature the 18K brings. You can check here the improvement about the loopback cable. So you have a plus of 40% in FIO, so which is a major improvement. I have just written some parameter about the FIO. The FIO parameter we use to run this benchmark. So nothing, it's magic, okay? We use a block size of 3 meg. For example, when you play with DCR, we have the notion, I don't know if many people know the notion of VRC which is a major key when you want to achieve performance on the 18K and on the this year, when you use this year implementation. Why? Because 3 meg, because the super stripe is 3 megabytes. So to achieve this result, of course, we hunt the latency in the system. So what we need is that we cut the I/O scheduler, for example, to be sure that we could have the max throughput. One other thing is we can say that Lustre is not bad, okay? But when we say that, I prefer to troubleshoot a bit more before to say. Because if you have the good configuration, you can say that the overhead is less than 1% against the raw device, so which is pretty low. So you have the configuration here if you want to reproduce, but Lustre is pretty efficient. To be honest with you, we can say that Lustre like clients. Okay, so if you want to have a good performance, we need clients. For example, on this case, we have 8 OST. We need 34 clients to have this pretty interesting overhead. Lustre improvement, like I have said, we know that there is some issue about unaligned I/O. Lustre Master brings some improvements. You have some numbers. We have big boost, for example, in the IOR hard benchmark, a jump by 5, which is not negligible, and we can do much better. The same thing with the MD test part. You have an improvement which is pretty linear. It means you can increase the number of MDT and the performance is scaling pretty well. To achieve this, you need custom patches, but it means that the code in Lustre is scaling. Okay, thank you. One time, the good news is that the IO 500 pushes Lustre and pushes improvement of Lustre. Lustre is more and more powerful. Just, it can be funny what I am telling you, but we have to work hard to have these results, and you can check how many people are involved in this project. For the IO 500, we have a guy from Atos, we have a network guy from CA, Damien Gros, we have Dominique, which is in my team, and of course myself. On the DDN side, about the contribution of the entire project, we have many people. It's not because I am in the DDN User Group, but it's true. Okay, you have many people. You have the president. You have the L3 support. You have engineering people, and so on. So many people work pretty hard to have a good and a power system. To conclude, we can say that the 18K story was pretty exciting. We achieved pretty good performance. I haven't told you, but 118KE, we are closed in IOR wide sequential workload to 78 gigs, which is pretty good. We have many things to do. We are discussing with DDN about the unmapped feature. We need some improvement. on the map feature. We need to insert, of course, in our store file system the 18 KE. We are doing right now CentOS Suite benchmarks. And the next step will be to do the same work about the 9012 enclosure. And of course, maybe a next IO 500 submission. Thank you. Questions?